Okay, so one of the things we're interested in on a telescope is the magnification. Magnification normally is expressed in terms of the ratio of the object to the image. And obviously if I'm magnifying it, the image would get bigger, and so magnification is normally the height of image divided by the height of the object. That's typically how it's presented, okay? We don't use that definition on our course because when you're using an astronomical telescope, the stuff generally is very small. So the normal way of representing magnification is in terms of something referred to as angular magnification, okay? It's a similar idea, but it's in terms of angles instead. I'm going to give you the equation off the formula sheet straight away and then just explain it using what we did when we made the telescope and then relating it to the ray diagram we did for the telescope so you can understand where this stuff comes from. Okay, so you look on the formula sheet under the astrophysics bit for M magnification is given by this. So angular magnification equals angle subtended by image at I divided by angle subtended by object at unaided I. It's the mother of all formulas. And I've missed off the M. M equals, so capital M is angular magnification or magnification. So the angle subtended and we used our eye and like that, if you recall, and we weren't using the telescope. So what you had was the angle subtended, and let me just do this a bit differently. So the angle subtended by the unaided eye, like that. So this is the window you're looking at. Yeah, and that's the angle subtended or created by the object at the unaided eye. I'm just using the eye. And there's normally a convention for the way that they show these, although they don't use these letters on the they don't use the letters in the formula, they use the words. And I'm just checking because I always get the wrong way around. They use B in here for the unaided eye. And they refer to this as beta in the textbook. It has been used both ways, which is why I'm checking. So beta is the name we give to the angle subtended by object at unaided eye. So beta, angle subtended by object at unaided eye. Okay. And you can see what we've measured, what you recorded when I asked you to, was this length here and that height there. And that will allow us, because you've got a little right angle triangle, to work out this angle as you'll do later. Okay? And you can see it's the same angle formed by the object there. Are you happy with that? So that's the object, or the angle subtended by object at unaided eye. In the telescope, what we had, so this was the ruler, this was our eye again, and the lens was there. And we had an image of the window in there. And again, draw this line in here. So that just goes like that. And this angle here is the lens on the telescope. So this angle here we refer to as alpha, and that's the angle subtended by the image. And again, I know this distance. That was 5 centimeters. I'm going to call that a centimeter. So I know that distance, and I got you to measure the size of the image. Again, so I've got that height there. So I can calculate what this angle is. Okay? So we can find alpha, and we can find beta, and the angular magnification is then the ratio of this angle to that angle. Or that angle, in fact, to this angle. Okay? Everyone happy with that? That's what they are. So what I'll do, I'll get you to work this out for your the telescope that we had. Then I'll go through how we can calculate what it should be using the focal lengths of the lenses. Okay, and I'll use the ray diagram from the telescope more or less that we did to show you where these angles come from and how we can work out this angular magnification. So from the measurements that you took, can you work out for me the angular magnification, or estimate it at least, for your telescope? Yeah, you've got 2 right angle triangles. The way I know, shall I walk through and get it calculated? Or okay, well, there's, again, for the purposes of the video, everyone's just gawping at me and no one's saying anything. So let me walk through it then. I'll show you how I do these, yeah? These questions are actually very straightforward because they're all the same thing. They'll try and complicate it by using different words and different information. But I always do this. I'll do 2 pairs of triangles, one like this, and then one like that. So this is the object. This is the image. That's the angle subtended by the object, beta. And this is the angle subtended by the image, alpha. And m equals alpha over beta. And then what I'll do, I'll put the information that I've got onto here and work these angles out. Okay? Or if it was an exam question, put the information I've got in the exam question to work something out. So typically what you get, you might have an angle subtended by the image. You have to work the magnification out using the focal length of the lenses, and then you might have the distance to some object, and you've got to work out the diameter of the object. Type thing, yeah. So when I did this, anyone got the data to hand? Or use someone's numbers? Okay, we got I'll do that when we talk about it. It doesn't actually, because the angle's small. 10?
So the length of my arm,
yeah.
For the length of my arm, I got 67 centimeters.
Image height was?
Image height was 4.5.
Sorry, 0.5?
4.5.
Are we talking about the old? This is the unaided eye.
Unaided eye, I still got close.
4.5 centimeters. Were you looking at the right window? It was through the gap. Yeah. I mean, no, so I got a centimeter for the window when I did it, and my arm's not that much longer than yours. Anyone else got value for the height of the object? And yeah, 0.8. I thought. How long is your arm?
56.
56. It's not that much different. Okay. I'll just check that out, Ted, because I think that's you meant to look at the wrong window. Height of the image you saw on the lens?
1.6.
Sorry?
1.6.
1.6. And this distance here would be about 6 centimeters. Now then, Greg said you need to use degrees or radian. When the angle's small, in radian, then that divided by that equals that angle. So it makes life very easy. If you want to go through the tedium of doing inverse tan, you can do. It'll make no difference to the answer in degrees. Yeah. So I'll leave it in radians. So in radian, then beta equals opposite over adjacent. And in fact, if you get given angles in the questions, they'll always give you the angle in radian. I mean, it comes from tan theta is opposite over adjacent when theta is very small, then tan theta is approximately equal to theta is equal to opposite over adjacent in radian. Yeah, so that's when it's small angle approximation. It's equivalent to saying that for the arc, I'm assuming it's a straight line rather than a curve, effectively. Okay, which is true for very small angles. So beta equals opposite, which is 0.8 divided by adjacent, 56. That equals that. 0.8 divided by 56 equals 0.0114 radian. And then alpha equals opposite, which is 1.6 over 6, equals 1.6 divided by 6, 1.26. Therefore, angular magnification is the image over the object, 0.26. This is going to be inclusive. I beg your pardon? Well, I was going to ask that question actually because I realised I didn't see what the units were. What do you think the units might be given the angles should be in radian? Sorry?
Is it radian seconds?
Radian seconds? I'm just saying radian seconds because the video won't pick it up. Radio seconds? Pretty sure? Pretty sure? Oh, no. Leon, yeah?
Just arbitrary units.
Arbitrary units, so like meters or degrees or...
Oh, no, I meant like units.
No units. That's different from arbitrary units, isn't it? So no units. So why would there be no units? Because we're doing everything in radian, look. Magnification is just usually a time. I'm just saying that because you can't hear what you're saying, Leon, yeah? And anyone else watching this in years to come, what did Leon ask? Yeah, what's he saying? And so I'm just highlighting here. Erica? Yes, so you're right, and that's how you figure it out, because the equation came from the angle subtended by image, angle subtended by object at unaided eye. That's in radian, and so the units cancel out. It's just a ratio, so there's no units. So it's just a number, yeah? And I should have said that when I did the definition. No units. So the angular magnification is 20. Can you work yours out and see what you get with your data? Because that's probably, well, it's a bit bigger than it should be, but it may be different for you. So can you work out what you got, please? Practicing.
Wait, no, I think I don't think it is.
I don't think that is.
Mine is. So where I'm thinking is the two values the other end.
Well, was that one is 6?
Is that what they're swinging? I'm just practicing it.
What's it meant to be?
We'll find out. Hey, Lloyd's asking what's it meant to be, and I said we're going to find out. We're going to calculate it using the focal lengths of the telescope. I just need to tell you how you find it out. That's all.
Are you gonna? I'm going to do that.
It's just lower than 90.
Objective was 50, and the eyepiece was 5.
There we go, 40.
I had it.
Oh yeah, I put 6 or something.
We got it then?
I got like 15.
There you go.
I got
10,
Like 15.
15.
Yeah.
Any more out the range between? I mean, we just got 19 with it's Billy, is it? No, what's it?
Even more.
It's Billy. What do you call it? Nate. Okay. Anything bigger than 20?
Yeah.
22.7. That's very precise, isn't it? Yeah, very good. Anything less than 10? Erica? 9. Okay. So somewhere between 10 and 20 then, yeah? We reckon. All right. Well, look. So I've simplified this down. This is the telescope, refracting telescope, in normal adjustment. So the two focal lengths add up to be the separation of the lenses. This is the image formed at this little focal point here. I'm trying to figure out what the angles will be. So alpha is the angle subtended by image, and beta is the angle subtended by the object at the unaided eye. So let's do the image first. So the angle subtended by the image would be that one. So that's that one. If you look at here, this is the angular size, which is also equal to that, which is also equal to this. You don't need to do this proof, by the way. I'm showing you where it comes from. So beta is that angle in there. I've got a little right angle triangle. The angle subtended by the object at the unaided eye, actually, if you had your telescope like that, and you're looking through there, really the angle is all the way to your eye from some object, yeah? However, when we're looking at stuff which is a long way away, like, you know, hundreds of thousand kilometers, it doesn't matter if I take the angle to the front of the telescope or the back of the telescope, because the telescope might only be a few meters long and I'm looking at something 100,000 kilometers away. So what I can do is, the reason for that is that this angle here will be the angle subtended by the object, more or less. Yeah, it should be at my eye here where I'm looking at it, but I'm going to do it this front of the telescope here. But because this distance is enormous relative to that, it's a reasonable assumption. So it means that this angle in here will be alpha. Yeah. So the reason I'm doing that is I've got two little right-angled triangles here with a common image. So if we do tan alpha equals alpha when it's very small, which is the opposite over adjacent. It's the height of the image. I'll call that h over f naught. And if I do tan beta equals beta, and it's approximately equals to beta when the angle is very small, which they are, then that's the height of the image over the focal length of the eyepiece lens. So we define the magnification as the ratio of the image over the object, which is beta over alpha. I've got to be really careful not to screw this up. So that means it's going to be beta, which is h over fe, h over fe, over h over f naught, which is ending up to be f naught over fe. So h's cancel out, that goes in the bottom, that goes in the top. So the magnification also equals the ratio of those two focal lengths. Guess what? We have that. Yeah? Everyone happy with what I've done there? Good? You don't need to know that derivation, you just need to know this. But I always think it's helpful to know where stuff comes from and how we arrive at these things. So that's where it comes from. So given that for our telescope, f naught was 50 centimeters and fe was 5 centimeters, the actual magnification of that telescope should have been 10. Yeah? Which is sort of what it was for Galileo as well. I think his was about 6 actually rather than 10. So it's broadly the same as Galileo's telescope. Okay, everyone happy with that? Okay, right then. So what we'll do now, I will give you like a work example, and I'll explain how you should do it. And then there's some questions. I'll give you a past exam question and try one from the book as well. Okay, which is why they're out. You can look in the textbook as well if you wish, as I'm going through this. Okay, right then. And I'm going to make this up, so it might be pants. So a refracting telescope. Rubbish pen. Refracting telescope has lenses that are 1.2 meters apart, with an eyepiece lens with a focal length, an eyepiece lens with a focal length of 55 millimeters. When the moon is viewed through the telescope, the image subtends an angle of, this is going to be quite large, but nonetheless, Crumbs. 0.0173 radian. If the moon is 350,000 kilometers from Earth, calculate diameter of the moon. That's as hard as I get. I mean, that's as hard a question as you get because of the number of steps you need to go through. The difficulty, honestly, is interpreting this information here. The first parts are relatively straightforward. It should give us a value which is broadly right, I hope. What I've not factored in is the magnification. So it won't be right actually. We'll probably get it by a factor of 10. Okay. So what do we need to do? I would, first thing when you get an angular magnification question is do two pairs of triangles so I can put the information on that I've got and then I can think about what I need to do. So you've got the two pairs of triangles, one for the object, which in this case is the moon, and one for the image. And this is beta, and that is alpha. What have I got? I'm trying to find this one, diameter. I know this length here is 350,000 kilometers, 350,000 kilometers. So in order to work this out, I needed to find this. In order to find that, I'm given this, that's 0.0173 radian, and I know that the angular magnification is given by the image over the object. I need an object. So, let's work it through. I'm trying to find this. I can find that if I know that. In order to find that, I'm going to use this information and the angular magnification. Okay? It's normally the extent of the questions. I made this more complicated because we don't know this one here. We need to work out what that is. So M also equals the ratio of those two things. And I've got this, but what I've not got is that. How do I find that? George?
I'm a bit confused.
What are you confused about, sir?
Well, last time you had M as beta over alpha, and now you've got
Have I? Yes, I have. Sorry. I get confused with the alphas and betas.
I think you did.
Sorry?
I don't think you did.
Did I?
I don't think you did.
You don't think I did?
No.
Lloyd doesn't think I did. Anna?
Exactly.
So yes, I did.
Yeah. Maybe you got it.
I think this is there's something confusing in the book. They've got, that's what it is, because they've got the angle subtended by image at I is alpha, angle subtended by object at under the eye is beta, and then I think if you look at their diagram, oh no, they haven't. So that's right. That's right. So my previous one was wrong then. It's alpha is the image and beta is the object. So I'm genuinely, I'm sorry. I as I said, I get really confused. I even checked the book and read this. So alpha is the image and beta is the object. Yeah, it doesn't matter really because you don't use alpha and beta, you only use the descriptions. So it's not like, providing you know it's this one divided by that one. If it's the other way around, it's going to get smaller. It has to be that angle divided by that angle, otherwise it won't be magnified. So I'm very sorry about that confusion. I'll have to get someone to edit that out. Have you now? Yeah? Sorry about that, George. And if I do make boobs like that, please, put your hand up and let me know, because I'm not infallible by any means. But I do need to find the focal length of the objective. How will I do that? We know the lens separation, and we know that the sum of the two focal lengths gives me the separation of the lenses. So F0 plus Fe equals lens separation. Now that's not on the formula sheet. You just need to know that in normal adjustment. Okay? So the separation of the lenses, or the length of the telescope, is the sum of the two focal lengths. So do you want to work that through and find the diameter of the moon then?